Hey everybody, it's Mr. N again, and here we go with more information here on perpendicular lines, and we're going to do a couple proofs that involve those. But let's talk about some of the things we need to know about perpendicular lines. You know that perpendicular lines are two lines that intersect to form right angles, and a right angle is 90 degrees. Perpendicular bisector of a segment is a line perpendicular to a segment at its midpoint. So not only is it perpendicular, but it bisects it. On a triangle, it doesn't have to go through the vertex. So if the three bisectors intersect, we'll call that the circumcenter, and we will talk more about that later. But right now, let me just explain a couple things. So if I have some sort of segment, right, the perpendicular bisector, not only will it cut this segment in half, but it will be perpendicular to it. And then here's what I mean by on a triangle. Suppose you had a triangle. Well, let's draw it just a little bit different. I want to extend that side out. Okay, so perpendicular bisector, if I went halfway through this and perpendicular like that, notice that it does not have to go through this vertex up here. Okay, and we know that the shortest distance from a point to a line, that'll be the perpendicular one. So basically, if I tell you to start at point A and walk over to point B, you're not going to go this way. You're not going to go, or walk to this line, sorry. You're not going to go this way. That's going to take, you could, but that's going to be a longer distance than if you go that way, right? The shortest distance would be straight up perpendicular to it. And then we've got a couple theorems here. If two lines are perpendicular, then they form congruent adjacent angles. And if two lines form congruent adjacent angles, then we know they are perpendicular. So if two lines are perpendicular, then they form congruent adjacent angles. Let me draw this out to you right here and right there. Perpendicular, right? So this angle is congruent and adjacent to that angle right there. So angle 1 and angle 2 are congruent and adjacent. And the converse is true as well. And then we've got the next one. If the exterior sides of two adjacent angles are perpendicular, then the angles are complementary. So it's saying over here, if angle 1 and 2, if these are adjacent and perpendicular, then we know that it's going to be complementary. And then we've got the perpendicular bisector theorem. If a point is on that perpendicular bisector, then it's equidistant from the endpoints, and this plays kind of important role. Let me show you this drawing. If I had some segment right here, and I put the perpendicular bisector right here. Say this is the perpendicular bisector. Wherever I put a point, whether it's right there, whether it's down here, whether it's way like this or really up close, and then I connect them. So if I connect this and this just like that, let's try that, and I connect it, then this segment will be congruent to that segment, just like if I did it right here, congruent, and those would be congruent. Down here, this segment would be congruent to that one, and this one to this one. This brings up with the fact that if you bisect, what this ends up telling us is if you have an isosceles triangle, right, and you bisect it right here, this segment, or draw a perpendicular from a vertex, you end up bisecting the segment right here. So these two will be congruent. So if you had an isosceles triangle and you drop this perpendicular, you end up bisecting that segment. That's what this theorem helps us to prove. Moving on over here, we have the linear pair perpendicular theorem. This is what your book calls them. If angle 1, this is what we just kind of did, but just a teeny bit different. We're saying if angle 1 and 2 here are congruent and this forms a linear pair, then they've got to be, this has to be perpendicular. So 1 and 2 congruent, linear pair here, that means it's a right angle. And this next one, if these two lines are parallel, right, your book calls it the perpendicular transversal theorem. if these two lines are parallel and this line is perpendicular to one, then it's got to be perpendicular to the other, and we've talked about that as well. And then this is the kind of like the converse of it. If both of these are perpendicular to this line, then these two have to be parallel. Now, as far as these constructions, all of these constructions I have in a separate video. So I encourage you to check that out because it's easier for me to do it in the other software. So here I'm going to make a perpendicular line from a point not on the line. Here I'm going to make a perpendicular from the point on the line. And here I just am doing a perpendicular bisector. All right, so check out the video on the perpendiculars and it'll help you constructing these. All right, let's do some examples, and I will do one proof for you guys today. Over here, given that these two are perpendicular, BE and AC, and then these other two are perpendicular over here, BD and BF, we got to find x. So since we know we've got a bunch of perpendicular things going on, let's see what we can solve for. Over here, the measure of angle 2. If I know that the measure of angle 2 is 2x and the measure of angle 3 is 40, well, I was just told that these are perpendicular. So that means 2x plus 10 plus the 40 equals 90. So over here, 2x plus 50 equals 90. So we'll finish this off with 2x equals 40 and x equals 20. On the next one, the measure of angle 3 this time is 3x plus 5. The measure of angle 4, again, now I know that these are perpendicular like this. So I can set these equal to 90. So then I know that 3x plus 5 plus the other 3x, so this one and this one, will equal 90. So 6x, and bring that over, 85. X will be, and that will end up being, 14 and 1/6. Okay, moving on over here to number 3. If the measure of angle 1 is 7x, the measure of angle 2 is 7x plus 6, so 1 and 2 will be a right angle. And the measure of angle 3 is 5x plus 12, and the measure of angle 4 is 8x. To find x, well, we just can do 1 and 2 over here because we know 1 and 2 will be a right angle. So let me just do this one on the side over here, and I'll just say that 7x plus 7x plus 6, this equals 90. So 14x will be this 84, which yields x is going to be 6. And you can confirm it by doing these two and setting these two equal to 90, adding them all, make them equal to 180. So there's more than one way to do that problem. And let's do this next one. The measure of angle 1 is 3x plus 1, and the measure of angle 2 is 4x plus 5. The measure of angle 3 is 2x plus 13. That's just extra info. All I need is these two because I know that's going to be 90. So 3x plus 1 plus 4x plus 5 equals 90. So 7x plus 6 equals the 90. 7x will be 84. And so we know x will be 12. Okay, moving on. This proof I'd like to do, here we go. Write a 2-column proof for this. You're given that these two lines are parallel. You need to prove that and angle 1 is congruent to angle 2. We need to prove that R and S are perpendicular. All right, so let's draw this out. We've got our statements here, and we've got our reasons. And step 1, we are going to write down the given. So R is parallel to S, angle 1 congruent to angle 2. This is our given. Okay, so we know that. So if R is parallel to S, we can say that the measure of angle 2 is congruent to the, so angle 2 would be congruent to angle 3, and this is by corresponding angles postulate, because if these two are parallel, then these corresponding angles must be congruent. But wait, if that would make 1 congruent to 3. So in this case, angle 1 is congruent to angle 3, and this was by a transitive step. So now if 1 is congruent to 3, that means angle 1 and angle 3 are a linear pair by definition of linear pair. Well, that means that angle 1 and angle 3 are right angles because they are congruent adjacent angles, right? Which means step 6, in fact, you could have just finished this off and didn't really need step 5. R is perpendicular to T because of that the theorem we just did, where if we have a linear pair that is adjacent, so adjacent, need this one, adjacent and linear pair form the perpendicular lines. And I think we called that linear pair, or its converse, that linear pair perpendicular theorem. I think that's how your book called it. All right, so we'll leave it at that, and we'll do the rest of the examples and stuff in class. So thanks for watching. Hit that like and subscribe button, and I'll see you guys in the next video.